All right, so we started talking about kinetic friction the other day. Now we're going to talk about static friction. Hopefully the word static tells you what it is. Static friction is the force that opposes sliding motion. Of one non-moving surface past another. So static friction is going to be friction between two things that are not moving, but there's still forces at play. A really great example is if I have a fridge on carpet, and I'm trying to push this fridge. So I have a force that I'm pushing it with, but it stays put because there's enough friction, static friction, holding it in place. So static friction can range from 0 to a maximum value and this value is determined by the normal force and the coefficient of static friction. But there is a maximum value because eventually I can push that fridge with enough force that I overcome the static friction and I give myself some sort of net force in the direction that I'm pushing. So static friction can be overcome. A stationary object starts to move when the applied force equals the maximum force of static friction. Once the object is moving, is it static friction anymore? No, static friction becomes kinetic friction. And that happens when? When the maximum static friction is overcome. Essentially, there's enough force that it negates or cancels out the force due to static friction. So we get a net force in the direction that we're pushing. So we have an equation for static friction. We're going to have the tiny f here for friction, and it's going to be S for static. And that's going to equal some coefficient of static friction. So we have this mu again, sub S, and it is also correlated to the normal force. So again, in this equation, we have static friction. That's going to be in newtons. We have our coefficient of static friction. And we have our normal force, which is also measured in newtons. So that's our equation for static friction. Now we're going to put this into practice. So here's our problem. Students design an experiment to determine the static coefficient of static friction. Could write out coefficient of static friction. I'm just going to write mu sub S. All right. And this coefficient of static friction between a pumpkin and the desk it's sitting on. So they're going to pour sand slowly into a bucket. So let's draw this out. And the book gives us a picture. So I'm going to draw this out. This is my table. This is my pumpkin. And then the pumpkin is tied with a rope to a bucket. So they're slowly going to fill this bucket with sand. Until the pumpkin starts to slide. So as soon as the pumpkin starts to slide, they're going to stop putting sand in. So as soon as the pumpkin slides, they stop putting sand in, and then they unhook the bucket of sand and they weigh it. And this sand weighs 11 newtons. So now our job is to determine the coefficient of static friction. So I know that my static friction is equal to my coefficient of static friction times my normal force. I'm going to draw a free body diagram of my pumpkin. So I have some sort of weight pulling it down, and I have some sort of normal force that's balancing that out. And then, let's see, we're going to pretend there's a pulley on the edge of this table, right? So we're assuming that this is a frictionless pulley. So because I have a frictionless pulley, if we use what we know of tension, we know that this force is the same across this whole rope, which means that our pulley is changing the direction of force. So our pail of sand has a force of 11 newtons downward, but this rope right here changes the direction of that force. So on our pumpkin, that 11 newtons is actually acting in a sideways direction. So we also have the weight of the pail or bucket. So the other thing that we need to remember is that our maximum static friction is going to be when something starts moving. As soon as it starts moving, that's when we have our maximum static friction. So since we're looking for our coefficient of static friction, I'm going to rearrange our equation to be mu sub s equals my force of static friction divided by my normal force. And we said that our force of static friction is going to equal the force that's causing it to move, right? Because right before it moves, we have something that looks like this. We have its weight, we have the normal force, we have static friction, and then we have the weight. And as soon as these things equal out, then it starts to move. So the assumption that I can make there, or the conclusion that I can draw, is that my static friction is going to equal the weight of the pail as soon as the pumpkin starts moving. And I know that my normal force is going to be equal and opposite to my weight, right? Weight and normal force, we don't have any sort of acceleration in the y direction. So I could also say that this n, my normal force, is equal to mg. Something that I forgot to label is the mass of our pumpkin. Mass of our pumpkin in the problem is a 1.8 kilogram pumpkin. So now I think I have enough to solve for my coefficient of static friction. Mu sub s equals the weight of my pail, which is already in newtons, so I don't have to do anything there. 11 newtons divided by the mass of my object, which is 1.8 kilograms, times 9.81 meters per second squared. When I do all of that math, it turns into 11 divided by 18 newtons, and then this all here, kilograms meters per second squared, is also equal to a newton. Otherwise, we could say, oh, well, I know my coefficient of static friction. Any coefficient of friction is going to be unitless. 11 divided by 18, my mu sub s is equal to 0.61. All right, we're going to do one more practice problem. When you push a 1.80 kilogram book resting on a table, a force of 2.25 newtons is required to start moving it. Once it's moving, it only needs a force of 1.5 newtons to keep it moving. Find both coefficients of friction. So this is going to be practicing both our coefficient of static friction and our coefficient of kinetic friction. Something that you'll notice is most of the time we have less force required to keep something moving than it does to start something moving. Our coefficient of kinetic friction oftentimes is less than our coefficient of static friction. So I'm just going to draw a quick picture, and we're going to start with our coefficient of static friction, okay? So this is my book on a table, and I have some sort of weight and some sort of normal force. And then I have a force of, let's see, we said 2.25 newtons. And then I have friction. In this case, it's static friction because my book isn't moving. It's pushing back on it. So now I have to figure this out. Let's start with some of our equations. My static friction, coefficient of static friction maximum, is going to be equal to my coefficient times the normal force, which I could also say my coefficient of static friction maximum is equal to mu sub s times mg, right? Because again, we don't have any sort of acceleration in the y direction, so my normal force and my weight have to be equal and opposite. So my normal force is equal to my weight, which is mg. If the book isn't at rest, or if the book is at rest and that 2.25 starts it moving, in the instant that it starts moving, we're going to have a maximum static friction of 2.25 newtons equals mu sub s times mg, which is 1.80 kilograms times 9.81 meters per second squared. When I do that in my calculator, I'm going to do the 1.8 times 9.81. That gives me mu sub s times 17.658. Now, to get mu sub s all by itself on this side of the equation, all I have to do is divide both sides by 17.658. And then the kilograms meter per second squared is newtons. So 2.25 divided by 17.658. I'm going to have a coefficient of static friction that is equal to 0.127. All right, so I'm going to circle that. I'm going to move it to the top here so that way I have room to calculate my coefficient of kinetic friction. So now we're thinking about kinetic friction. My weight and my normal force are going to stay the same, right? Because my book is still the same mass. So my normal force and my weight aren't going to change. But the difference here is now I have a 1.5 Newton force. And if I think about the way that the problem is phrased, it says the book is moving with a constant speed, okay? That's the assumption that we're going to make, is that when it says keep it moving, it's moving at a constant speed. If it's moving at a constant speed, we don't have a change in our velocity. If we don't have a change in our velocity, our acceleration is going to be 0. If our acceleration is 0, our net force must also be equal to 0. So the sum of forces in my x direction equals 0 because it's moving at a constant speed. There's no acceleration. Equals 1.5 newtons minus my kinetic friction, right? Because I also have kinetic friction that's counteracting or opposing that 1.5 newtons. So my F sub k also has to equal 1.5 newtons. It's just going to be in the opposite direction, right? This minus indicates that they're in opposite directions. So now I'm going to use my equation. My kinetic friction is equal to my coefficient of kinetic friction times my normal force. Well, we just said my kinetic friction is going to be 1.5 newtons is equal to my coefficient of friction times, and then our normal force, we just calculated already, and that doesn't change, 17.658. And this was also in newtons. So now I can divide both sides by 17.658 newtons. So I'm going to take that 1.5 and divide it by 17.658. And I'm going to get a mu sub k, or coefficient of kinetic friction, that is equal to 0.085. So now I have my answer, right? I have my coefficient of kinetic friction, and I have my coefficient of static friction. That's the end of this video. Hopefully you have the tools now to solve for coefficients of static friction and coefficients of kinetic friction.
Can I go to sewing today?